Hey guys, it's Josh from LeetDev, and today we're going to do LeetCode Weekly Contest 216. As you can see, the contest has ended already, and that's because we were all busy Saturday. I was playing D&D, Scott was doing something else. However, we will tackle this anyways, see how we do, probably embarrass ourselves, and then learn all the algorithms and patterns that we might identify that might show up in a coding interview in the future. So let's get started. As you see, LeetCode has a nifty feature where we can use a virtual contest. And so we'll just do this as it is the real thing. Let's see what happens. So pretty exciting. I assume we're starting. So let's start with the first question. And I'll just close these and I will maximize the screen. So the first question, check if two string arrays are equivalent. Given two string arrays, word 1 and word 2, return true if the two arrays represent the same string and false otherwise. A string is represented by an array if the array elements concatenate in order forms the string. Okay, so this is basically a string comparison of a concatenation of the words in the array. So we have given example A, B, and C, and AB, and then second index C for word 1, and word 2 we have an array of a string of A, and then another one of B and C, and we add them together and they form ABC, and as a result, that returns true. But in example 2, word 1 is A, and then CB, while word 2 has AB and then C, which are not the same. Okay, so it seems straightforward enough, and typically, as you can see right here, it's a LeetCode easy question. So for easy questions, generally, there's nothing too involved. It's honestly just doing a brute force solution would probably give us what we need. So for this example, I think the best way to accomplish this is we could just build a string. Well, if we were smart, we could probably join these two arrays together to give us a full string and then just compare them. But I'm sure that wasn't the point of this LeetCode problem, and they wanted us to do something. They wanted us to actually iterate through the elements in the array. We could concatenate them, and that would give us I believe probably like an n squared, maybe an n cubed solution. I might have to double check on that because every single time we, at least in Java, add strings together, we are basically creating a new array. So that's itself is a n operation, and we do it, let's say n times, so that's n squared. So that's n squared. Yeah, n squared solution. Yeah, n squared. I don't think it'd be much better. So we'll just do it. We'll concatenate. But, since it is a point, we are timed, which I probably shouldn't have spent a lot of time talking. Should have just started writing. So I'll just be lazy. And we'll just do exactly what I just said. We'll say word 1, say word plus equals string word. We're just going to do a for each loop through both of our arrays. And now that we have the concatenation and everything, we just do w dot equals w2. Very important Java that we use dot equals. We compare the actual content versus when we're comparing the actual instance or the pointer. So that works, and typically it'd be actually smart. I'm pretty confident this is the correct answer, unless they're going to. Oh, actually, they already gave a whole bunch of examples. Oh no, this is the test example. So yeah, so we ran this, and we ran the example that have given us, and we got it true, false, true, which is exactly what is expected: true, false, true. So I believe this answer is correct. Yep, accepted. So let's go on to the next one. Maybe I should just go first. All right, so next question. Small string with a given numeric value. Oh boy, it's a medium problem. So the numeric value of a lowercase character is defined as its position 1 index in the alphabet. So the numeric value of A is 1. Okay, so alphabet A through Z, 1 through 26. The numeric value of a string consisting of a lowercase character is defined in the sum of its character's numeric value. For example, the numeric value of the string ABE is equal to 1 plus 2 plus 5 plus equals 8. And that makes sense because A is 1 and B is 2 and E, I guess, is A, B, C, D, E is 5. Yeah, so that gives us 8. Okay, so we're given two integers n and k and return the lexicographically smallest string with a length equal to n and numeric value equal to 8. Lexicographically smallest string. Okay, so I guess that means start with the smallest letters, which is the case in this output, A, A, Y. It looks like we just want this to be alphabetical. And we want the value to equal k. Okay, so we want to make a letter that is of size n that letters adds up to the value k. Okay, it's definitely harder. So I wonder if this can be like a dynamic programming question where we just try every combination. We start from A and then we go A and then we go to index 2 or the next value, and then we calculate, and then we just randomly pick everything starting from A through Z, and then we go there and we continue going until we hit n, and then we just keep calculating. But then keep calculating, but then I'm not sure about how we would keep the cache. I mean, I guess it can probably work. It'd be interesting to see how many times I have to repeat. But another idea that came to me is that since this is an important key hint to this, I think, is it wants it to be lexicographically the smallest string. So that sounds like to me, and just looking at the values, that sounds to me maybe we want to be as we want to have a greedy solution of some sort where we would try to pick, maybe go backwards and then start with the largest letter that we can pick and then continue adding it afterwards. Yeah, I think that might be a good idea. So it would be something like, gosh, how would we do this? So if k is 27, then that means we could pick the z. Z is 26, and that would give us 1 left over. And of course, then that'd be too small, so that doesn't work. Right, and that's fine. Then we'll just, maybe it's still a recursive solution. We would pick our letter and then we just keep going, but we'll start going backwards, and I guess we can just reverse the string afterwards, and that's not a big deal. So let's say we start with something like, we have a recursive solution. We start with k, or this is pseudocode, nothing official. So we would start with, I don't know, let's call it a function called helper for now. And I'll just start this public. I'm not quite sure what we'll return yet, so I'll have to say string for now. I'll call it helper. N, we have our int n, and then we have our int k. So at this point, I think we would recursively try everything, or go from the end to the front. So our base case we would try to hit is if n equals -1, and that means we have an answer. And then if we have an answer, we would just return. Yeah, that means we hit our goal, which means we maybe just return nothing at this point. And then otherwise, we would say we have k. Otherwise, we are currently counting one of the numbers, and then we have our k value. So I guess what would make sense is we would we have a for loop, and we go through everything from basically 0, or I guess A through Z, so 1 to 26. So I guess we can say for int I equals 1, I less than equal to 26, I plus plus. And of course we'll probably do some smart checking and see, you know, if k is less than 20, if our I value is greater than k, then we just skip, and we just probably return nothing. But then we would probably at this point do something like call our helper, we do n-1, and then we would do k minus I. And I would guess that we would get a result back. And then if our result is empty, well, I guess we would probably pass something back, but it would be, I should just go down. It would be, and then maybe if we're given a valid value or something, then we know we can continue. Yeah, but we have a value, and then I guess we need some way to figure out if the answer is correct, or if we traverse through everything. But the idea then is, you know, once we get our string, our res back, if our res is valid, we continue going through our loop. Otherwise, we would probably do something like return res plus, you know, the character we chose, which probably you know, while since I did this, how do I compute a char into a, I think it's a and plus I minus 1. Yeah, that's what we do. Yeah, so a would be a ASCII character and a char, and then we would subtract I minus 1, or we use I, which would then, or we add I, which would then convert it to the next letter. But because I is 1, we want it to and I represents A, we want it to stay the same, so we have to subtract 1, so that A, which is at the value 1, would actually become 0. So A, the char value of A plus 0 is itself, which then would give us A. So we would concatenate that into our list. Yes. So I guess since we're doing this greedily, in fact, we might not even, actually, forget the whole recursive solution. Honestly, I don't really know what I was thinking. We don't really need the recursive, because if we actually just want to find the biggest value at first. So we don't want to start at 1. We just want to start at 26, and then we want to keep going until we hit 1. So we go backwards. But then we're doing it like this way, and we're doing it the most optimal. We don't really even need to recursively go through everything. We can just pick the value, and I think an answer is always guaranteed. It didn't say so, but I believe an answer is always guaranteed. So if that's the case, we don't even need to go through this whole recursive function. We just need to just start subtracting our k value. We just need to find the next biggest value that would fit our k value. That would leave space left over. And then we can just keep building it from there. And of course, we have to consider how much n is left. So we can't just use everything. Yeah. Yeah, actually, so yeah, that's a better solution. So that's what we'll do. So we can ignore that whole entire mess. Let's say string. We could use a string builder, but just for the sake of getting an answer out first, I'm going to, well, okay, I'll be honest, I probably won't use a string builder, but if you want to be more efficient, we use a string builder. I'm not, I'm just going to build this here, or just concatenate onto string and then reverse it. I might have to change the string builder anyway, so I can call the reverse. It's whatever. Anyways, so we'll start with I equals 26. We'll continue until I is greater than or equal to 1, and then we'll go backwards. Or I guess we'll do I equals 0, I less than n, I plus plus. So the idea is that, so we'll iterate through all n items, sending it from the back, and then we want to pick the biggest, which is 26. So we say if our current k value minus I is still greater than n, because we don't want to, if you look at our first example, we don't want to use everything. Just because we can fit 26 into k doesn't mean we should, because n is 3. No, we might actually make more sense to start from n and then go to greater than 0. Greater than 0. But like I was saying, we don't want to just use the biggest value, because we want a string value of 3. So if our k is 27 and we pick z, that'd be 26. So we have one left, and I'll probably just type it out. 26, and that'll give us 1, but then our n would still be, we still have 2 left over. We still have to pick 2 characters, and that by default only gives us 1, and we don't have space for that. So we have to make sure that the biggest value we use is actually greater, will give us enough space for our n values. So k minus I is greater than n, and I think it actually should be greater than equal to n. Right, because if it's 27 minus 26, this would be 1, and we want to be 2, so that wouldn't work, but if we chose y, that would give us 2, and that would give us space to use RA. So yeah, we'll do that, and then if that is the case, we found the value, then we do the same thing that we talked about here. We cast a, I don't even think we need a cast, honestly, actually, because it's always a char. So, and that would give us this, and then we can just call a break to exit this for loop, and then we'll just continue going until eventually we get our answer. But then our answer will be backwards. So what we have to do is we have to reverse it. So at this point we have the string, so let's just say string builder equals new string builder, and just give it our answer, and we say answer that reverse, and we'll just return that. Now, of course, if I was doing this optimally, I would have to start with the string builder, or maybe just start an array, a char array, and then just build it backwards. But let's see if this compiles. That's a compiler. Oh no. Int I equals 6. Variable I is already defined. Oh, yeah. The first mistake, we used I. And we don't want to use I right here. We actually want to use J. A minus J. Or want this to be I, not N anymore. I guess we could subtract N. I don't think it wouldn't matter too much. And oh, yeah, it's not answer, it's builder. All right, let's try this again. Cannot be converted to string. Oh, yeah. And then toString. Yeah, right. All right, let's see how this goes. Ooh, judging by its time to exceed, it's probably going forever, so that's not good. So that would mean that... So it's probably here. Yes, it's here. We want to subtract and not go up. There we go. Okay. So we have this. Okay, we have this gigantic random string, and that's probably because we did actually need to convert this to a char. There we go. Oh boy, okay. Well, we converted it, but now we found a problem in the sense that it's not the correct letters. And I'm guessing the reason is because our if statement, we're probably picking very large numbers. Oh, you know, I was right. This is K. So it has to be larger than... No, that's correct. One thing I did forget to do is since we have a valid value, we still need to subtract our J value from it. We need to subtract the value from J, yes. And yep. And then we can continue. Okay. Getting closer. Is it J minus 1? I don't think so, because this is all J based. It's less than or equal to I, so it's actually I minus 1, because in the first instance we have 3, so we don't actually want 3, we're actually comparing to 2. There we go. AOI. So yeah, maybe not the best case. Probably should debug in person, but you know, that's what it is. All right, so 320. So our answer is AAY AASCZ. So I believe this is the correct solution. Could throw in test random cases since it's a contest, but I think I already ruined a lot of this by just talking. So I'm just gonna submit and see what happens. I think the only potential problem that I might run into is if you throw some very weird edge cases. Or I mean, not edge case, but yes, a time limit exceeded. Yeah, when we're testing very large numbers. So like this 96149. So we just have a very large case because this equation, this algorithm itself is n times 26. So I guess the question is, maybe it doesn't want to go through this second loop. It is a constant, so technically it is n, but it's still, there's a large amount of numbers, so that could take us a while. I wonder how much I'm doing on time too, actually. So instead of doing 26, so another way of doing this is, honestly, we don't even need to guess all 26 letters, because we already know what letter we should be using just by what's left over in our K value. So the value we should use is, let's see if we can think this out loud, but really at the end of the day, we really want our value to be, I don't know, let's do it, int answer, and we have our K, and then it is K. Well, the idea is that we want K to be 20, we want 26, or we know that if the value is larger, I'll just write this down. If K is greater than, the key is K minus I. Yes, K minus I. Let's do this right here. K minus I. If K minus I is greater than or equal to 26, then we want to use a Z. Now, if K, otherwise, if K minus 1, K minus I is less than that, less than 26, well, I mean, basically it's just an else at this point, then we basically just want to use Well, it's basically this, that, right? We just have a char, and then we just say a, and then we just say plus k minus 1. Or k minus I. And we still need to convert it, so we still need to subtract 1. And we don't really need this for loop. And that would give us the same thing, and that would give us the most optimal every single time. Expected. Why is there expected semicolon? Did I forget semicolon somewhere? Oh, it's an else. Else if. Okay. So we're kind of getting there. It's not exactly, but we're getting there. So, well, first mistake is we want it to be greater than or equal to 0 at this point. We don't want it to be that, and k minus I, actually, all right, okay, again, there's easy y, okay. Oh, and it's the same problem every single time. We still don't subtract our k value. God dang it, always forget to subtract. Actually, it's basically just our k minus, oh, we might be subtract 26. Here, it's a bit more complicated, and we actually subtract k minus I. And that should give us AYASCZ. Yep, okay, that gives us that. So now, instead of foolishly hitting that submit button one more time, I will just put this answer here, and we'll see what happens. If we're lucky, okay, there you go, it compiles. All right, so that's good, that's very promising. And I believe if I hit submit, it will say we're good. Oof, 10 makes 60, but it just passed. It just passed. Okay, so another interesting idea is the problem itself actually has nothing to do with this. It's just with the fact that I don't think it can honestly get any more optimal than what we have here. So if that's the case, and we're having this problem, then that most likely means that our array itself is the issue. So we can make a char array, and then we'll say new char, and it has to be size 26 or of n. And then instead of doing this, we'll just say char at index I equal our answer. That's what I get for trying to be lazy. Is z. And this we can say, and it's also I equals char, subtract, and then instead of building up all of this again, we'll just say anstat. I always forget. Let's see, how do I convert a char array into a string? I think it's array.toString, and then you pass in the char, or maybe you can build the string builder, but I cannot remember. That's a compiler. Wait, I still have answer plus equal. Where do I have answer? Oh, yeah. Okay, well, we got that. Oh, it's a string to array. I can't remember. Value of, and we'll just give this, and that should give us the answer again. So this time we have this. Now the question is, will it be good enough to pass the time restriction? Let's find out. Finally! This is what I get for being lazy. Oh my goodness. I'm not even. I just not even. All right, I wonder how I'm doing on time. Oh wow, I have 56 minutes and 36 seconds, 52 seconds left. I think each contest is 90 minutes. So we spent 30 minutes working on 2 problems. As you see, the top answer was 12 minutes, so I stumbled through this one. This one already gave me the best answers, or this guy already like completed everything. That's awesome. But you know, it's okay. We're all going at our own pace. So we're going to tackle question number 3, ways to make a fair array. Oh god, what happened here? I'm gonna refresh this. There we go. Okay, I don't know what happened. Okay, you were given an integer array nums. You can choose exactly one index. Notice that's 0 index this time, and remove the element. Notice that the index of the elements may change after the removal. For example, if nums 614741, okay, if we choose to remove the number 1, that will give us this array. Okay, and if we choose to remove the second index, that gets rid of the 7, that gives the remainder. Okay, makes sense. And then the numbers after that would swap and they'd be even and odd. So it's very important to keep that into consideration. An array is fair if the sum of the odd index values equal the sum of even index values. Return the number of indices that you could choose, such that after the removal, nums is fair. And fair being that the sum of the odd index is equal to the sum of the even index. So this question in itself is interesting. So the brute force solution obviously is we have would be like it'd be an n-squared solution. We just pick the index that we don't want to count, and then we just iterate through the remaining elements of the array based off of if they are odd or even, and then we count them. I'm pretty sure an n-squared solution is not good enough for this, and that no one will. Well, that's not true. I feel like these contests can surprise you. Maybe they'll actually let that work, but I suspect that's not the case. We'll find out. The more optimal solution, I wonder if we can be an n log n solution. I somehow doubt that's really going to be the case. Don't see how we can sort anything, or yeah, I don't see how we can sort anything or do some division or divide and conquer. I could be wrong. So one thing that did cross my mind, I've seen it in a problem a long time ago. Don't really quite remember the idea behind it. I think it was like a DP problem. But we have a sum that we keep track of. I imagine be like an odd or an even sum. And then as we iterate through and remove indexes, we would subtract or add. And then by keeping track of these sums, we can easily we can figure out how to, or we can figure out if it's fair or not if we after remove each index. So to illustrate, or more like help me even try to reason about this, you have 61741, and so if we have a odd sum of oh yeah, we just keep count of our current odd sum. So I assume 0 is 164. So yeah, 1 and okay, so this is index 0 and this is index 2. Okay, that makes sense. So it's even by index. So even, we would have 6 plus 7 plus 1, which would give us 16. Odd is 1 plus 4, which would give us 5. So for example, so we would have the sum, and let's say we go through this, we pick the first value, and let's say we remove 6. So we have to remove one thing. So let's say we remove index. There's only one answer, right? You can remove any. Oh no, it's fine. Oh, the number of answers, that works. Okay, that makes it fair. That makes sense. So yeah, so there's the n-square solution. Same idea applies. We just have to go through everything. We have to keep track of the answer. The sums are fair. But this is an optimization, assuming if my memory serves me right. I feel like kind of confident about this, but we'll find out. But yeah, so we have this. So let's say we remove the first index, so that's 6. So we make a even value, or we remove the first value, so it's a even number. So we remove that. So we would have, I mean, I feel like this is kind of right. I just don't know the idea. It'd be 10 and 5. So we know that this answer is not fair if we were to remove 6. But then the interesting part now is how can we infer anything for any future iterations? So we jump to 1 and we remove 1. So what does that mean? So index 0 equals false. If we remove 1, this is the 1 case, we would have 6, which is still even, 7, or 7's odd now, and then 4 and 1. Or no, that's gone now. So actually no, I'm completely wrong. If we remove 6, then our even would now be 1, 4, 1 and 4, and our odd would be 7 and 1, which is 5 and 8. So now the question is, how do we infer anything from this? One interesting thing that you can note that just happened is that our odd flopped and became our even. Now, whether or not that is, or let's make this crazy. 1, 7, 4, 1. Yeah, 1, 4 instead of 1. So it could be a coincidence, but these numbers swapped. That gives us 5. Now, what's interesting is how did this give us 8? And it gives us 8 because I did this math wrong. 6 plus 7 plus 1 is not 16, it is 14. Okay, so it's interesting because then now we see it flopped. So yeah, that's good to know. Potentially it could be very valuable. So let's say we get rid of index 1. That would give us an even number of, and this would give us 6, 7, 4, 1, and this would give us 6, that's 4, which is 10, and odd is 7 plus 1, which equals 8. So it's interesting. I wonder, is there a reason why the odd stayed the same? Or I even did that right. But our even changed. Even, odd. And remove the first index. So I think one thing is interesting to note is that our previous, all the values in the back that we calculated, like the 6 and I guess 1 if we continue counting, will remain the same. So it's kind of like we have a after and a before that we need to keep track of, if that kind of makes sense. So we have an even before, because no matter what happens afterwards, that 6 will always be an even number. That'll be 6 guaranteed. And I guess we'll have a odd before too, which right now we haven't counted anything odd yet, so it's still 0. And so at this point, okay, I feel like we're getting closer to something. So now we're counting our even. We already have our even before, everything that we know is guaranteed to be even, which in this case is 6. plus our new even value. So we have this list of even numbers that we counted. I wonder, we have an after, right? So because we are removing a odd number, everything in our, actually, I guess not an odd number, but if we're just removing a number, everything we have, I imagine, would flip. So all even sums would become odd and all odd sums would become even. So what we really need to do now is we have our 6 value, and then because we removed 1, our 1, which is a even value, our odd value, all of our odd value becomes even. So all of our odd after value becomes a even, and all of our even value becomes odd. So that would give us 4, which then would give us 10, and our odd value, which was 7, 1 for sure before, previously even, but then because we cut it out, they get flipped, so it becomes 8. Yeah, and I believe this gives us our answer, right? 6 plus 4, which are even. Yeah, okay, this is good, this is promising. I feel like this is close to the right answer. Excuse me. Let me check I'm recording everything, actually. I'd be very sad to see that I'm not. Okay, good, I am. Yeah, so I think I got the gist of it. So we would calculate a even, I don't know, after and a odd after. And we would count a even before and a odd before. Or yeah, I don't know. So the befores would be all the numbers that we've already passed, so they would all start at 0. And then all the afters are the values that we encounter that we'll be gradually removing from and adding to the before and after. That we would, I guess depending on what index we're using, we would just interchange them. We would flop the evens and the odds. So I bet if we were to, so right now, as you can see, we flopped the values for odd and even for index 1, and that's because everything was odd. So we sliced an odd number no, I believe that would actually that would be the same no matter what. Yeah. So we would always flop these numbers, the befores and afters every single time. And I think that would give us our solution. We would keep track of our afters. Well, we first calculate our afters, and then as we iterate through removing each of these indexes, we would remove those values from we would add all the even befores with the odd after and the odd before with the even afters, I believe, because removing that specific value would always change. And then we would move the specific index that we're on. Let's in this case we remove 1, or index 1, we would just remove 1, which is also index 1, from the, I guess, the even after pile, or it's odd, so the odd after pile, and then add it into the odd before, because from that point on, it doesn't matter what we remove. 6 will always be even, and 1 will, if for example we're index 2, 6 will always be even and 1 will always be odd. Yeah, and then we'll just keep going until we reach it, and then we just compare the sum between these two values, and that'll give us the answer. And this would be a O-event solution, and I guess it's like it is kind of like a DP solution because we are keeping track of the values and changing them as we go along. Yeah. Alrighty, so that's the algorithm. I'm actually surprised I came up with this, but having some past inspiration was very helpful. Now the question is, can I implement this? All right, let's give us some space. Take a water break. So I guess we have int even or int odd before. These values will be incremented as we continue. Int even odd after. You know what? I'm not going to question their naming sense. All right. So that's what we have. And so the first thing we would do is we want to calculate our evens, our after values. So then plus. Now if our I mod 2, yeah, come on, is 0, that means it's odd, it's an even number. If it's an even number, we say even after plus equal nums at I. Otherwise, we are a odd number. We say odd after nums I. Okay, so now we calculated our before and now we calculated our odd and even after numbers. We can start going through everything. Yes, we still use I because we want to keep track of what index we are on. Okay, so yeah, now is where our algorithm begins. So just like what we talked about, so we need to first get our, well, we're slicing the value that we're using out. So in this case, I equals 0, 6. So I'm just going to define everything. E equals nums at I. So we're slicing the 6 out. And so all that's left for us is our before and our after. So our odd values will be our odd values. If we just had in this case it is 1, 7, 4 and 1. Our odd values now would be 7 and 1, which were before our even values, which makes sense. So we'll say int odd equals our even after, and then of course, just like we talked about before, we would add that with our odd before, because nice. Why am I typing Python syntax? Oh, well, it's too late now. Guess I'm typing too much Python at work. Anyways, that's fine. And then we have our even, which is our odd after plus our even before. And that would give us our odd and even value. And then we would just say, and of course we also have to keep track of our answer, our actual answer, which is 0, or our fairness. So if odd equals even, then we return, or we increment our answer by 1. So that's how we calculate that. But then, so that's our first iteration, but now we need to adjust our values. So if if the index we're on, mod 2, equals 0, that means we removed a even number, and now that we are moving on to the next one, that number still exists. So we're going to add that to our even before. That's our val, yep. Otherwise, our odd before, add our val. And that would give us, yeah, those are store before values. And then the last thing we also need to do is we need to update our after values so that whatever this one belongs to, so that we no longer account for them there. So if we are removing a even number, or since we're storing that there, I think the correct thing to do is to just remove it from our even after and our odd after. I'm also mentally drained right now. It's been a long time. So I will just assume and let the compiler figure out, tell me if I'm right or wrong. But I think that's roughly it. And then we just return the number of answers we counted. And let's see. So clearly 2164, I assume, is wrong. The answer should be 1. That's disappointing, especially since I thought this was pretty good. Okay, so it might have something to do with this even after. So let's go back to the example that we had. It was 6174. So we know that our even after at this point was 671, and our even odd after is 1 and 4. So this would give us 13, 14, and this would give us 5, right? Yes, 14, 5. So we started at this point, and we said we remove 6. Oh, you know what the problem is? We never removed the first problem is that I didn't actually remove the value from our even after or even before. So that's an issue. So the first thing we need to do actually is we can say if I mod, I really should just make this Boolean, equals 0. That means we're removing the even number, so we should say even after minus the val. And so we don't actually need to subtract it here. We actually have to subtract it before. Yes. All right. So we do that. Otherwise, we do odd after subtract the val. And then, right, then we remove this. And then it'll be 7, 1, which then would be our odd number. And then we would have 1, 4, which would be our even number. Yeah, I believe that's what the problem was. Oops, forgot to put the semicolon. All right, there we go. Okay, that was the mistake. Now let's see how the rest of this runs. 130, 130. Wow, this might actually be correct. Boom, there you go. And that is how I would do this after many attempts at debugging. But awesome, yeah. All right, we got this. So let's go to the final question, which is a LeetCode hard. And I know from my own past track record, it took us 30 minutes to do that one. So which actually wasn't bad. Like, you know, if this was a interview question, we might have like, depending on the interview, you might get an easy question, or this might be your question, and then you get follow-up. Now is my time to get a follow-up question, to answer follow-up questions. So I'm actually quite happy with this. Anyways, so typically at this point, a lot of my past experience with doing hard questions, this is usually when I give up. Usually never successfully solve a hard question. So there's that, but let's give it a crack anyways. Minimum initial energy to finish tasks. Yeah, I'm brain dead. And I'm at the point where I'm so tired that I don't even want to try anymore. So I think for this contest, I'm going to call it good. We're going to look at curious to see how I might have done. Oh, hey, it does tell me. Okay. Yeah, so it's not bad, not bad. Just with what I got, I would have got 1670 out of 5700, so that brings me at top 1/3. Definitely don't see myself as being super awesome like these fine folks over here, but I don't think that was horrible, especially since I haven't did like a contest in a long while. All right, let's just quit and see what happens. If you want to give up, your requirement will be deleted. What? It'll be deleted. All right, well, that's unfortunate. I might just leave this here, but you saw it first. Top 33 percentile.